So this is a very small code. And with the help of this code, I want to demonstrate to you the filter operations. Right? If you recall yesterday, what we said is neural network is kind of a representation learning where the layers which are closer to input side, they learn the core features. So what I meant by saying core feature is typically in any image, the edges, the boundary, right? So those features are nothing but the core features. Now, once we have learned the core feature, we will be learning some more high level feature. So in the subsequent layer, once they have learned the edges and the boundary, they will understand how to connect these edges and boundaries together. And further after that, the subsequent layer will learn how to connect these parts to frame some object like eyes, nose, lips, right? So in this way, a neural network learns. It starts with pixel values. From that pixel values, it understands the core features. It keeps on combining those core features to understand sophisticated part like eyes, nose, and that is how a face is recognized if I'm trying to solve a face recognition problem. Okay. So how do we learn these core features? Is for that there's a very important role of filters. Okay, so this filter which I'm going to show you now, this will be used to detect the edges of an image. Okay, and again here the library which I'm using is OpenCV computer vision. I'm going to use NumPy array, and I'm going to use Matplotlib for visual display. Okay, I am starting with image which is in PNG format. This is how my image looks like. So I loaded this image into my system. You can see here I have this image, right? This is how my image looks like. So this is the logo of OpenCV, right? And I want to detect the boundary, the edges of this image, right? So first of all, I need to define my kernel. So what I'm doing here is I'm creating a square matrix where all the elements are ones. Okay, and I'm multiplying it by -1. So this is how my this first of all this kernel would look like. Here, let me write this one and this. Okay, so this is how it looks like. It creates a square matrix, right? And all the elements are -1 because we have multiplied each element by -1. And after that, what I'm doing is I'm putting 8 in my center of this square matrix. So I'm replacing this 1, 1 position by 8. So if I do this here, you'll see that yeah. So this is how my filter is created. So if you recall in yesterday's class, we have seen this filter. Exactly this filter we had. Where is that? So here, yeah, right. So this kind of filter we have created, right? So this is a slightly different filter than this. This filter will detect the edges. So how this filter will operate is, it boosts the current pixel value, the pixel value over which it is operated, and it suppresses the neighborhood pixel, right? You see, this 8 will boost the current pixel and it will suppress the nearby pixel value. And if we apply this over an image, you'll see that if I'm applying this filter to this image, you'll see that my only border, my edges will be detected, and rest all pixel value will become 0. That's why you're getting rest all places there's a black background and only the edges is determined. You're able to see this?
Yeah, I can see. So the way I'm understanding is that because those the pixels in the picture, they will be the -1 is basically reducing their values, right? But
Yes.
the center one is increasing it.
Yeah, the center one is increasing it. It is boosting, the rest are suppressing.
So these the pixel value, I mean the arrays of the image, they will
Mhm.
contain values between 0 and 255, right?
Yes.
So there's some random numbers, right? 255, 251, 191. So for
Mm.
every 3 by 3 square,
Mm-hmm.
this kernel is being applied and one is being subtracted from every element, and from the
Yes.
center element the 8 is being added.
Yes.
But then you were saying yesterday, right, that the resultant matrix will be the summation of all of that that will be
Mm-hmm.
applied to the top left number.
Mm-hmm. Mm-hmm.
Same thing is happening here.
Yes, same thing is happening here.
Okay.
Right. So, so this is a one filter which detects the edges. Similarly, you can create some other filter which will, instead of detecting the edges, it will blur this image. So that's what I was talking yesterday. All this modern image uh, editing software, they they use filters only. It's all the game of filter. They apply filter and that generates different effects on your images, right? So typically this is what happens with CNN also. In each layer we apply some filters to learn some features, some core features about the image, right? So if in the first layer of CNN, if you apply just filter, you'll get to know the edges, the boundary of your images. Okay. And as the layer proceeds, you will learn more features like this, and ultimately you'll learn how to combine these different attributes together to frame the actual image. This is how a network learns.
Can you repeat?
Okay. So see, in CNN, in convolution neural network, you'll have lots and lots of layer, right?
Yeah.
So when I'm applying this filter on my first layer, so in the first layer, I learned how the boundary of my images looks,
Yeah.
right? When the output of this first layer will be fed to the next layer, right? In that layer, I learn some other features of images. Again,
Yeah.
the output of that layer will be fed to the next subsequent layer. In that layer, I'll learn some other feature of it. So in this way, I keep on learning different attributes of my images, and ultimately I'll understand how these attributes are connected together to form the composite image, right?
Yeah.
So that's how the learning happens in case of CNN, convolution neural network. Okay, you
And
can
CNN is specifically for images only, or it applies to other areas of
it is specifically utilized for image problems.
okay.
Okay, you can apply deep neural network also, feed forward network also for image detection, but that is not recommended. I'll talk about why it is not recommended. Although we have said yesterday that in case of feed forward network, there are lots and lots of weights and biases, right? And more the number of learning parameter you have, higher the chances of overfitting you'll have.
Yeah.
So CNN has got the capability of generalizing the complex feature, provided that in case of CNN will have lesser number of learning parameter. That's why CNN is preferred, right? Just think that if you have to do an image detection using feed forward network, so each of your pixel value will have one feature, will be considered as a one feature, right?
Each pixel value is considered as one feature, you're saying?
Yes, if you have to solve a computer vision problem using feed forward network, so so how the feed forward network works, in your input layer you'll be providing x values,
X inputs.
right?
Yeah.
So each of your pixel will be one x, it will be one feature, right?
Yeah. Yeah.
So if you are dealing with one SD image where the pixel values like 1024 cross 1024, Just think that how many number of inputs you'll be having here.
100,000.
That means this much number of input you're putting, right? That would
Okay.
make the problem really, really computationally expensive. Okay. So you understood like how using the filters we understand the wait,
No, so I understood what the filter is doing,
Mhm.
but then in the end you said that a regular image will have so many pixels, so the input becomes such large and it is
Mhm.
computationally very expensive.
Mhm.
So how are these two things related? Like this example that you gave versus
Mhm.
what you talked about, getting this edges
Mhm.
using that kernel.
Mhm.
Are you trying to establish some relationship between the two?
Yes, that is my eventual goal. But I'm not sure whether I'll be able to make that distinction clear in this class. But gradually,
Okay.
that is what my intention is. My intention is to show that for image, CNN is the preferred choice, and why it is preferred choice. That also I want you to understand, and how exactly we are doing a computer vision problem or image related problem using CNN in a better way compared to feed-forward network. Okay.
Yeah. Okay.
All right. So we have understood how convolution operation works in case of image, right? So if this is an image, right? So what will happen is we are putting our filter. So this is here my 3x3 filter. I'll be putting a filter on this image. Okay. I'll be performing convolution operation, which is nothing but think as a dot product, and I'll have one single value after that computation, and that value will be replacing this value, right? And same thing will do for all the pixels. Now one correction which I want to make in my statement here is, whenever we are putting the filter, when we are performing a convolution operations, after performing a convolution operations, we won't be replacing the value of this uh, pixel, rather will be replacing the value of this pixel, right? Just think that you have to superimpose your filter on top of your image. If I do some annotations, that will make more sense. Yeah. So this is, suppose your kernel of which is of 3x3, right? I'm applying this kernel here such that your this kernel center element is coinciding with this center element for this superimposition position. Okay. And after performing the convolution operation, this pixel value you have to update with the convoluted result. Once you have replaced this value, just slide this window slightly left by 1 unit, and now you'll see that the position of kernel is here. Okay. And now,
So one question, Ashutosh. So you're saying middle value, middle pixel is being updated, right?
yes,
But actually everything is getting updated, right? We are taking dot product, so each square, from the kernel side versus this pixel square,
Mhm.
they will all get the dot product. So the middle pixel, same thing as you said, that will be the summation of all, and the middle pixel will be updated by the summation of all of that, right?
Yes,
Okay, okay.
this is not getting updated, right? This will not get update. This will not get update because whenever we are putting our filter, uh, whenever we are putting our filter here, right? What is the center element? This is a center element, right? So
Hmm.
center element will get update. If I want to update this pixel value, then in that case, I have to put my filter like this.
Yeah.
Right? My
No, but
drawing,
why are you saying they are not getting updated, right? I'm saying everything is getting updated because that kernel is applying on all the 9 squares, or on the 9 pixels. The 9 pixel from the kernel are
No, no.
superimposed
Yeah,
on the 9 pixels from the pixel, from the image pixel, image, the pixel
yes,
from the image.
yes, you're correct. It is getting applied on all the 9 pixels, but but update operation you're performing for only this pixel, right?
Yeah, update we are performing for that, which is nothing but the summation of the rest.
Yes. So rest all thing
Basically
will remain
summation of
same.
everything.
Yeah, rest all thing will remain as it is. Only this pixel value will change. Okay, let me take a real example, and I think that will help to make my point here. Because if this thing you understand well, no, CNN is nothing. This is okay. So for time being, just understand I am having an image whose dimension is 5 cross 5. Okay. So this is my 5 cross 5 image. Right? This is 5 cross 5 image. And this is my kernel, which is having dimension 3 cross 3. Okay. So first of all, this kernel I'll apply to this position. Right? Correct?
Yeah.
You can think. Mhm.
Yeah, correct. Okay.
Now perform dot product of all the elements which are here. So let us give some values also. I'm giving each of my value as 1 image. Okay. So that my calculation will become easy. Right. And here I'm saying that this is also 1 okay, just the random values I have taken. Okay, now when I'll perform a convolution operation, what will happen? What will be the update? What will be the value? 1 into 1
9.
1, right? So total 9. So
9.
so the result of this operations I got as 9. Now what
Yeah.
I'm saying that you replace this value by 9. Rest all everything will remain same.
So when you say replace, what I'm understanding is once you are updating this kernel on top of it, it is going to create a new matrix which will have only one square where 9 will be there. Rest of the other pixels are gone.
Rest all pixels are having same value. Everything will remain as it is. Only this pixel value is updated by 9. You're not
So you're
getting.
saying that this 5 cross 5 matrix still exists?
Yes, it still exists.
Okay. Because so what I was thinking was once this dot product is applied, that is resulting in a single pixel which is of value 9.
No,
So
no, no.
thereby the resultant matrix is actually becoming smaller and smaller because this 9 by 3 by 3 matrix was reduced to a single pixel. Then the next one it moves, so that will become a single pixel. So that is not happening. The
No,
matrix is
no.
remaining as is.
Yes, yes. So first
Okay.
of all, you have to do this convolution operations for that entire image. So we have just
Okay.
done one iterations, right?
Yeah.
In the next iteration, what will happen? This window will move this way,
Yep.
right? And now you'll see that this one will be replaced by 9.
9.
In the next iteration, you'll have this way, and
Then
you'll
that will also be 9.
9, right? But now I cannot move after this, right? Because my image has over now. Now I do not
Yeah.
have any column after this. So what will happen? It will now slide downward. So the next thing it will have is like this. Now, and now you'll see that this will get updated as 9. After that, in the next iteration, you'll see that this will get updated. After next
And then
iteration, this will get updated. Again, it cannot go beyond this point, so it will slide downward, right? And after that, this you'll see that this will get updated. Next iterations, this will get updated. After this get updated, got updated, right?
Yeah.
Yeah. So what is happening is right now with the logic which we have learned till now, only total out of that entire 25 pixels value, only 9 got updated, right? This these things, these pixel value, they did not get update,
Yeah.
right? So what will happen is if we keep on doing this thing by layer, if I keep on applying filter, you'll see that the dimensions I'm having is will reduce in every subsequent layer. So from 5 cross 5, now it has reduced to 3 cross 3, right?
Why are you saying it reduced? It is still there, right? It's just
Yeah,
that the
it is.
values have.
Yeah. What we want is we want that every pixel value should get updated. If any pixel value is not getting updated, that means what? It's like we have not done any operations on top of it, right?
Yeah.
So that is the case which we do not want. Effectively now, if in effect, what we can say that now the meaningful information we are having in this image is only in 3 cross 3 matrix. Although we are having still matrix 5 cross 5, but the meaningful information is there only in 5 cross 5 matrix. Sorry, 3 cross 3 matrix.
Okay.
Okay. So again, if I'll apply, so now this is 3 cross 3 matrix, right? If I say this 3 cross 3 matrix. Now if I apply filter on top of it, right? Now you'll see that only this value will get updated,
Yeah.
right? So this is the case which we do not want. We want that every value should get updated. So for that, what I need is I need to put some artificial layer on top of it, on bottom of it, on left hand side and right hand side. So just think that if we'll apply some a layer on top of it here also, like this, right? Even though the value is 0 for all. Now in that case, I can update this value also.
Which value?
This one, the value which was not updated in my first iteration, this value,
Yeah.
right? If I'll, so this process is called padding. And this padding is of what? Degree 1, because I have added one more layer. I should not say it's layer, one more rows on top of it, on bottom of it, on left hand side and on right hand side. So now this will perfectly fit and I'll be able to update all my values. Now if I want, my kernel will fit this way, right? And I'll be able to make update on this position also. I'll be able to make update on this position also, this position also, this position also. So if I do padding, then I'll be able to make updates on all my values. None of my rows will be left without update.
So our 5 cross 5 matrix is all updated then.
Yes. By doing just one padding. Okay, so this process is called padding.
But is it not expensive? Like if you are increasing the memory, right?
I'm just adding one more layer. I mean, one more rows. It is nothing.
Okay.
Okay. So that's how typically we perform in real case scenario. Okay. So if this is an image, right, and if you have to perform a convolution operations, right, so this way you'll do it. First of all, you will do convolution operations, and you will replace this value. So this is just a snapshot of it, the process that we have discussed here.
So what, can you go back to that image? Why it is getting smaller? Like what are you trying to show?
Just now, what the point which I mentioned, no, that in every in after every filter operations, this will get small.
Oh,
If-
okay,
if
okay.
you are not do padding.
Yeah, if you don't do padding, it keeps getting smaller and smaller.
Yes.
Okay.
Okay. Now, so far, whatever we have seen, that is for the 2D case. Now let us slightly move to the 3D case. The 3D case means what? The image is now your RGB. The image you will have, it will have a 3 matrix, which you can think as a superimposed one upon other. And each of the matrix corresponding to one channel. The channel are RGB, red, green, blue. Okay. So again, when you are having an image which is having 3 channels, so now you can think it as a 3D, right? Now you'll have width, length, and depth also. Here the depth is 3 because I'm having 3 channels. Okay. So in this case, my kernel will be also 3D kernel, right? So same thing I have to do. It's just that my kernel dimension has changed now because I'm having a 3D image. Again, I have to fit this kernel over this positions. I have to perform a convolution operation. I have to move from left to right and top to bottom, right? And update the values. Okay. So even though my input is 3D now, my filter is 3D now, but after the convolution operation, the output that you will be getting, it will be 2D. Because after convolution operation, we get a single value, right? So my output will be here 2D only.
Why? Because the dot product of a 3D matrix will also result in a single value, and that is why it is becoming a 2D matrix.
Yes, yes. So how it happens is this is the result after doing convolution operation with one filter. Now, if you are doing same thing with another filter, then again you will get a some sheet like this, which will be in 2D in nature.
Hang on. So you're saying you're applying another filter on the output again?
No, on the same image. So this sheet you are getting after doing convolution operation with one filter. This is that filter. Now I am again doing the same operation. It's just that my filter is changed.
Okay.
The matrix value is changed. But still you'll be getting another this 2D sheet.
Yeah.
So what I'm saying that in real life case scenario, one input layer, one input image is convoluted by multiple filters, right? And we get a multiple output corresponding to each filter operations. We stack all the output together.
So you're saying we are applying multiple filters to the same image. So we are getting multiple outputs.
Yes.
Then we are stacking all the outputs together.
Yes. You can think like this. So there is a one filter which is doing the edge detection. There is another filter which is maybe doing some other operations. Maybe it is sharpening your image or some other attribute it is learning. Right. So ultimately we have this multiple output sheet corresponding to one each filter operations, and at the end we are stacking them together. Right.
Okay.
So this output you're getting at the end is still 3D. If I have to summarize, let me summarize this once before I actually move ahead. Your input is 3D here. Do you agree with this?
Yeah.
The filter is now 3D. Do you agree with this?
Yes.
But the convolution operation that we are performing is still 2D.
Yeah.
Right? We are sliding vertically and horizontally. That is also fine.
Yeah.
Right? And after getting the value, after getting the output, which is a 2D, we do this for multiple filters and we stack them together, all the output sheet. Okay, so that is how it happens in case of 3D image, RGB image. If it is a black and white image or if it's a grayscale image, the operation we have already seen. There you will have only one channel.
But Ashutosh, in case of multiple output filters, right? So
Mhm.
when you're applying multiple filters, you're getting multiple outputs which are 2D, and when you
Mm.
stack them,
Mm.
why are you saying it's 3D, right? It is more than 3D then. If it is 4D, it is
No,
4D.
no. See, just think you have a paper, right? A paper of some notebook. Okay, that is a 2D, right?
Yeah.
If I give you another paper and I'll just ask you to put that paper under the another paper which you had, right? It will be still, it won't be a 3D, it won't be a 2D. Now it is getting some depth also. So similarly, if I
Yeah.
ask you, you put 1,000 number of papers one below other, now it has become a 3D, right? It has got length, width, and some depth also.
Yeah.
So same thing is happening here also. So when we are applying a filter operation, the output is one paper, you can think, one sheet of paper, one paper sheet. And after that, same thing when we are doing it with other kernel, again I'm getting a sheet, I'm stacking all this sheet together. Now it has become a 3D.
Okay, yeah, I see what you're saying. But then where did this RGB go then? The channel values, where did they vanish, right? When we are doing this, are we not getting rid of these channel values?
No. Channel value will remain as it is. So channel value will be there with input image. Now, after applying this convolution operation, right, you're getting something else.
Oh, okay. So input is still there. We are getting some output. We are stacking it together,
Yes,
and that output is like again now like a 3D matrix.
yes, 3D matrix.
Ah, okay.
Okay, I know this is complicated. It's very difficult to understand it in one go, but trust me, I'm trying to explain this in the easy way. But it's perfectly okay if you're not getting in first go. But so far, are you with me?
Yeah.
Okay. Now, okay. So this is the same thing. Same visual representation of things which I just mentioned. You will be, so typically an image is convoluted by multiple filters, and you'll be getting multiple output corresponding to each of your filter. You stack them together and the output becomes 3D. Okay.
Can you come again?
So any image is convoluted by multiple filters, right?
Yeah.
For each filter, you'll be getting one output.
Yeah.
And that output will be 2D.
Yeah.
Right? Similarly, you have to do convolution operation with multiple filters. So you'll be having multiple output, which each output will be 2D, but when you stack them together, it becomes 3D.
Yeah.
So my final output you'll have that will be 3D.
Yes.
Right. Okay. So here I'll just quickly walk through, and in the next class, probably we'll see the concept of padding and stride in detail. So input width, what I'm saying, input width is WI. So in case here RGB image, the width is 3.
Yeah.
Height H1 and width is WI, depth is 3. Depth means what? Channel. Right? My input image width is W1. This is the width. Okay, this is the height. And this is the depth.
Yeah.
Okay.
So depth is a channel number.
Yeah, channel number. So here you can think the depth is 3 because I'm